Hello guys, today we are going to discuss about discrete mathematics, the application of discrete mathematics in Boolean algebra, computer networking, electrical circuit, electronic circuit, etc. First we will discuss about block 1. This block consists propositional logic, second methods of proof, and third Boolean algebra and circuits. We will study one by one or discuss one by one. First is proposition. What is proposition? Any declarative sentence is a proposition and it is universally either true or such sentence is also called a statement. All statements are sentence but reverse is not. Each proposition is denoted by a symbol. For example, suppose man is mortal. This sentence is a declarative sentence and everyone knows it is true. So it is universally true. There is no any confusion about this sentence. So it has value true. And if it is a declarative sentence and it has some value like either true or false, then it is a statement. And this statement is denoted by a symbol. Suppose it is denoted by a small m, etc. Then it is a statement. But all sentences, one of the sentences, such sentences is also called a statement. And all statements are sentence, but its reverse is not. It means like go there. It is a sentence, but it is not a statement because it has no any true or false value. You can't say whether it is true or false. So such type of sentence is not a statement. To be a statement, we must have a declarative sentence, and that declarative sentence has some true value or false. It means true values may be either false or true. Then it is a statement. Why it is not a statement? Because it is a command statement. Or any example of propositions are: the sun rises in the east. When we read this sentence, we can immediately decide whether it is true or false. Everybody would have the same answer. So this sentence is either universally true or universally false. It is a statement. I have told that declarative sentences are statements, but all declarative sentences are not a statement. For example, women are more intelligent than men. Someone says it is true, someone says it is. This sentence is declarative, but it is not acceptable as a statement or proposition in mathematical logic, because some people may think it is true while others may disagree. So it is neither universally true nor universally false. So such type of declarative sentence is also not a statement. That's why I have told you that all sentences are not statements, but all statements are a sentence. Logical connectives. There are different types of logical connectives that are used to connect two statements or two propositions. Each statement is also known as a proposition. So any statement that is denoted by some symbol, that symbol is a proposition. If there are two propositions, suppose there are two propositions P and Q, then the disjunction will be P join Q. This disjunction is denoted by symbol P, and it is known. It is read as join. So P join Q is a new proposition that has either true value or so. There are a number of different logical connectives like disjunction, conjunction, negation, and exclusive disjunction. They are either binary or unary. Binary means this operator or conjunction needs two propositions. If any connectives that needs two propositions, at least two propositions, then they are called binary. Otherwise, it is unary. Second logical connectives is conjunction. It is also binary. Third one is negation, unary. And fourth one is exclusive disjunctions or binary. Basically, above three are basic logical connectives, and it is the derived connectives from these two. Let us discuss each connectives one by one. First is disjunction. What is disjunction? If there are two propositions like P and Q, then the P join Q is false when both P and Q false. Otherwise, true. Suppose there are two propositions P and Q. Then it has four different representatives. Both may be false. First is false. Second is true. First is true. Second is false, and both are. These four are known as the interpretations of these two propositions. So, to find the total interpretations of the propositions, there is a formula. That formula is 2 to the power number of propositions. Here number of propositions is 2, so 2 to the power 2 equal to 4. So there are four different interpretations or four different values for P and Q, and we find the disjunction of these two propositions, that is P join Q. And this rule says there are two propositions, suppose P and Q, then P join Q is false if there are two propositions P and Q, and this is false when both P and Q false. When both P and Q are false in first row, so its result will be false. Otherwise true, and in all other cases it will be true. So its truth value will be T T T, and this is called truth table of P join Q or P disjunction Q. So finally, the truth table of this this disjunction is shown here. There are two propositions P and Q, and there will be four different interpretations: true, 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 false, false, true, and false, false. You can write either true, 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 false, false, true, and false, false, or you can also write false, false, like previous, our discussion. This can be also written like false, 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 true, true, false, or false, true. Both can be used either this way or either this way, and its value will be given here. This definition says if both are false, then its disjunction will be false. Otherwise, if its disjunction will be true. And if we write true, 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 false, false, true, and false, false, then both P and Q are false in last row, so its disjunction is false, and in all other cases it is. Second is conjunction. The definition is if there are two propositions P and Q, then the P conjunction Q or P meet Q. Conjunction is also known as meet. So P meet Q is true when both P and Q true. Otherwise, it means if there are two propositions P and Q, then P conjunction Q or P meet Q will be true. It will be true when both P and Q are. And just I have shown you, if there are two different propositions, then there will be 2 to the power 2 equal to 4 different interpretations or 4 different values of P and Q. They can be written like this. First propositions is shown by false, true, false, true, means alternative way 4 times. False, true, and second propositions is written like false, false, 2 times false, and 2 times true. So this is a way to write the different values. First variable is written as alternative form, false, true, or true, false, true, false, true, false. And second propositions is written like double 2 times false, 2 times true, or this can be also written like this: P and Q, P meet Q. First one true, false, true, false. Second 2 times true and 2 times false. Both are same. The representations are different, but both are same. There are 4 different values in this case also, and there are also 4 different cases. You can write either this way or this definition says if P and Q both are true, then it is true. If there are two propositions P and Q, then the P meet Q is true. When both P and Q true. When both true, it is shown here. So it is true. And false otherwise. So At all places we put false. False. Similarly, if you write in this way, then it's both values are true in first row, so it is true, and in all other cases it is. Finally, its truth table are shown here. This should be in a small. There are two different propositions, P and Q, and its total interpretations are true, 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 false, false, true, false, false, and both are true. So P meet Q true, and in all other cases they are. Third connectives is negation. If there is a proposition P, then the negation of P is false when P is otherwise true. It means if there is a proposition P, then its negation will be denoted by this not P, or it can be also denoted by 7 like this. Both are true. So there are two different ways to represent the negation of any propositions. Either we can use this symbol, or both are right. So if P is true, not P will be false. If P is true, then it will be false, and if it is false, then its negation will be true. Just opposite of the P. Negation is just opposite of P. If P is true, then negation of its P is false. If it is false, then its negation will be. It is very simple. The truth table of this negation is shown here. If P is true, then its negation will be false, and if it is false, then its negation will be. The next connective is exclusive disjunction. The definition of exclusive disjunction is if there are two propositions P and Q, then the P this exclusive disjunction, or XOR, it is also known as XOR, P XOR Q is false when both are same, otherwise true. Suppose there are two different propositions P and Q, then its exclusive disjunction Q. Since there are two different propositions, so its different interpretations will be true, true, false, alternative way, true, false, true, and it is 2 times true and 2 times false. The result of P exclusive disjunction Q, or P XOR Q, will be false if both are same. The propositions P and Q, its exclusive OR is false when both are same. Both are same in two different rows, T, T, F, F. So in this case, it is false and otherwise true. If it is different, then it will be true. So this is the truth table of exclusive OR, that is P exclusive disjunction Q. Its truth table is shown here. TT false, TF true, FT true, FF false. Here it is same in P and Q are same in first row and last. So in this case, it is false by definition, and in all other cases they are different, so it is true. That is shown in this table. There are another connectives. They are called conditional connect. First is P join Q. P implies Q. So P implies Q. It is also known as if P then Q. P implies Q. P is sufficient for Q. There are three different ways to read it. We can either say P implies Q, or it can be also read as if P then Q, or P implies Q, or P is sufficient for Q. There are three different ways to read it. In this proposition, where P is also known as premise, hypothesis, or antecedent. In this, there are two different propositions. Left proposition is known as premise, either premise or hypothesis or antecedent. And Q is known as conclusion or conceit. It means we write P implies Q, then left one proposition is known as premise or hypothesis or antecedent. There are three different ways to read it. Antecedent, and this Q is known as either conclusion or conceit. So each proposition is known by a different name. Left one is known as either premise or hypothesis or antecedent, and right one is known as conclusion or consider. Another conditional connective is known as P double implies Q. It is read as P implies and is implied by Q, either this way, and P is necessary and sufficient for Q. It is also known as biconditional, if and only if, or IFF, or two-way implication. So there are different ways to read it. We simply say P double implies Q, or P implies and is implied by Q. P is necessary and sufficient for Q. Biconditional, if and only if, IFF, or two-way implication. P if and only if Q, or we can say it P implies and is implied by Q, or we can say P is necessary and sufficient for Q, or we can say P biconditional Q, or we can say P if and only if Q, or P if Q, or we can say also P two-way implication. So there are a different way to read it. Now we discuss one by one conditional connectives. P implies Q. P implies Q. If there are two propositions P and Q, then the P implies Q is false when P is true and Q is false. It means if hypothesis is false and conclusion is true, then it is false, and in all other cases it is true. What is the meaning? P and Q. There are two different propositions, and P implies Q. In this case, P is a hypothesis or antecedent or premise. Generally, we say it hypothesis, and Q is called conclusion. It says when P is true and Q is false, then P implies Q is false. If there are two different propositions P and Q, then P implies Q is false. P implies Q is false when P is true and Q is false. First, write the total. First, we write the all interpretations of P and Q. There are two different propositions, so total propositions will be 2 to the power 2 equal to 4, and they can be written like this. We can use either true false, or false true or false. I have used here true false, and 2 times true, 2 times false. So these are the 4 different interpretations of P and Q. And the definition says if P and Q, there are two different propositions in which P is true and Q is false. P is true and Q is false. There are two different rows where P is true and Q is false. Q is false in two different rows, this and this. But both conditions, P true and Q false, is shown in second row. So in this case, it is false, and in all other case, it is true. I think it is clear to you. If there are two different propositions P and Q, then P implies Q is false when P is true and Q is false. Otherwise, it is true. So there are 3 different true values and 1 false value. And to get false value, the hypothesis must be true and conclusion must be false. So left one is known as hypothesis and right one is known as conclusion. So in this truth table, P is true and Q is false in second row. So its truth value is false, and in all other cases it is true. Finally, its truth table is shown here. P and Q, there are 4 different interpretations as I have discussed you earlier, and in this truth table, P is true. P is true and Q is false in second row, so its value is false, and in all other cases it is true. As our definition is, if there are 2 different propositions P and Q, then P implies Q is false when P is true and Q is false. P is true and Q is false, then it is false. Otherwise, it is true. So this is the truth table of P implies. Second conditional connectives is P double implies Q. The definition of P double implies Q is if there are two different propositions P and Q, then P double implies Q is true when P and Q both are same, otherwise true. Otherwise it is false. Suppose here P and Q, two different propositions, and P double implies Q. So total interpretation will be true, false, true, false, true, true, false, false, 2 times true, 2 times false. And the definition says if P and Q are given, then P double implies Q is true when P and Q both are same. The truth table of this P double implies Q is shown here. Since Q is first proposition, so it is written true, false, alternative way, and 2 times true, 2 times false. Second proposition is written as 2 times true, 2 times false. And you know, P implies Q is false when P is true and Q is false. When P is true and Q is false, so P implies Q is false, and in all other cases it is true. And in case of Q implies P, Q becomes hypothesis and P becomes conclusion. So Q is true and P is false. In third row, so it's Q implies P will be false, and in all other cases it is true. And P double implies Q is, by definition, if both are same, then it is true. P and Q both are same in first row and fourth row. Then it is true, and in all other cases it is false. So here it must be false. And the second way to represent P implies Q is P double implies Q is also written like this. P double implies Q is equivalent to P implies Q and Q implies P. We will discuss in details about equivalent. If left side formula and right side formula are same, it means if the truth values of left formula and right formula are same, then they are called equivalent. We will discuss in details about equivalent in later classes. That's why I have shown here P implies Q and Q implies P. If we add one more formula here, P implies Q, and Q implies P, then from this truth table there are P implies Q and Q implies P, and you know by AND connectives that if both are true, then it will be true, otherwise it will be false. So here both are true in first row, so in first row it is true, and in second row it is false and true, so it is false, and in third row true and false, so it is false, and in fourth row both are true, so it is true. You can compare here the truth values of this formula and truth value of this formula. Both are same. So true, true, false, 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 and true, true. So this is a second way to represent the P double implies Q. And this definition P double implies Q says that if there are two propositions P and Q, then P double implies Q is true when both P and Q are same. Otherwise, it is false. So finally, we conclude that it is false. We finally conclude that by this definition, if P and Q there are two different propositions and both are same, then its result will be true. And if they are different, in this case they are not same, then it is. There are more symbols. They are called logical universal quantifier. It is denoted by this symbol, and it is known as for all. A formula is given here. px, where x square is greater than 0. X is where x is non-zero integer. For this value, if we take x equal to 1, then it will be 1, which is greater than 0. If x equal to 2, then it is 2 to the power 2, 4 is greater than 0. If x equal to 3, then it is 3 to the power 2, that is 9 is greater than 0. So for all non-zero integer, for all non-zero integer of x, this formula is always true. Then it is denoted by for all. But if for any one values it is not true, then it is not called universal. There are another logical quantifier that is called existential quantifier, and it is denoted by reverse of e. There exists. It is read as there exists. And in this formula, qx, where x is the parameter and it is x plus 6 is greater than 11. It is not true for all the integer value of x. Sometimes it is true and sometimes it is false. So this type of concept is denoted by existential quantifier. It means if there are 100 different items and all are true, then we use for all. If any one is false, then it is denoted by existential quantifier. Okay, we will discuss in details about logical quantifier in later. There is a logical equivalence. When the truth values for each interpretations of left and right formulas are equal, then they are called logically equivalent. There are a number of different formulas which are logically equivalent. Suppose E double implies G is denoted by E implies G and G implies E. This table is important for students because one or two different formulas are given in any term and examination to prove the formula by using truth table. So this table is very, very important for the students. So write down this table or note down this table and try to prove this logical equivalence formula. The truth values of this will be equal to this. Similarly, the truth value of this is equal to, and any one formula can be given to you in term and examination for proof. If it is given like E implies G is equivalent to not E join G. So here two different propositions are used, E and G. So its total interpretation will be true, false, 2 times true, 2 times false. And you know not E will be the reverse of this E. It is true, then false, true, false, false, true, false, and E implies G. E implies G is left hand side, E implies G, where E is hypothesis and G is consequence. You know, when a hypothesis is true and consequence is false, then it is false. In second row, it is false, and in all other cases, it is. This is the truth values of left hand side, and in right hand side, I have to use not E join G, and you know it is false when both are false. Not E is false in two different rows. They are shown here, and G is false in second and fourth row. So both are false in second row, so it is false in second row, and in all other cases it is. You see here, left hand side formula is equivalent to right hand side formula, that is E implies G is equal to not E join G, because the truth values of E implies G is equal to truth value of not E join G. True, true, false, false, true, true. So these two formula are equivalent. Similarly, all other formulas are equivalent, and it is generally given in a term and examination to prove its equivalence formula. Thank you.